Hi, I'm Oyeka, Department of Electronic Engineering, University of Nigeria, Nsukka. Welcome to my presentation on impact assessment of physical activities on an inkjet printed body-mounted UHF RFID tag. This is the outline of the presentation. We'll talk about a general overview of RFID, RFID on humans, why inkjet printing, tag design, simulation and fabrication, test scenarios, test results, and conclusion. First of all, what's RFID? RFID belongs to a family of contactless identification systems, which includes barcode, QR codes. It doesn't require any line of sight, which means it has higher speed and higher capacity. You can read a lot of tags at the same time. It works with the principle of backscattering, which I'll discuss in the coming slide. It's expected to be a major player in the field of Internet of Things because of its relatively low cost and low power requirements. It's found it can be used in inventory management, personal tracking, access control, livestock management, and so many other things. It's also a very valuable market, valued at $12.5 billion as at 2018, and it's expected to increase further between 2019 and 2027. So the principle of backscattering is simple. It just requires an RFID or a RFID reader known as an interrogator sending RFID signal to a tag or transponder. This tag comprises of the tag antenna and the application specific integrated circuit or ASIC. Upon the RF signal impinging on the tag reflects back the received signal to the reader, but the reflected signal is modulated, aiding it to encode information. So this is a very simplistic overview of what's happening in backscattering. So you might be wondering, why use RFID on humans? There are so many reasons why you would use RFID on humans. To start with, for medical reasons, where it could be an embedded device or as a sensor monitoring the overall well-being of an individual. It could be used in a personal tracking in office environments or a factory. It could be used for access control when you want to restrict access to a particular place or room in a building. It's also a component in the increasingly popular body area network. It's also can be found in Internet of Things, as mentioned earlier, where it can be used as an environmental passive sensor, also in human behavior analysis and gesture recognition. Human body affects RFID tags in two ways. The first is dielectric loading, which leads to increase in electrical length, hence tag detuning or change in frequency, and also lowering of the tag impedance. The second is absorption, which leads to reduction in radiation efficiency of the tag. This is caused by water molecules absorbing the RF energy and leading to a limitation in the available power to the tag. So why would we use inkjet printing? What are the benefits? The first that comes to mind is its drop on demand feature, which prevents wastage. This is because you actually deposit ink on a particular part of the design where you need the ink to be. This when compared to conventional etching where the unwanted parts are etched away. It saves wastage. It also has high precision. You can print as little as 200 microns. You can get a good conductivity, about 56% of conductivity of bulk silver. Then it's also very flexible. This is a very important feature, considering that if something is attached to the human body, you want the person to be comfortable. You want the object attached to be able to move according to the movement of the skin. You don't want any discomfort to the individual wearing this tag. So flexibility that inkjet printing provides is very important. This is an image of the inkjet printer. It's a Dematic DMP 2831 series. Inkjet printing doesn't come without issues. It has some issues. The first is difficulties with print resolution. This is caused by the ink spreading when you deposit on certain substrates, especially on porous substrates. You can have the ink spreading, which means maybe if you want to print a 200 micron track, due to spreading, is going to be more than the intended 200 microns. It has substrate limitations. You can't use inkjet printing on all sorts of substrates, especially porous substrates. So you can use it on wood and some types of paper. You also have concerns about conductor skin depth losses, which means you have to deposit more than one layer of ink to be able to satisfy skin depth requirements if your tag is going to perform optimally. This is an overview of the tag design, simulation, and fabrication. So the simulation was done on CST Microwave Studio. The slot design, the tag is a slot design. The slot design is good because as the field intensity plot shown on the upper right diagram shows, you have a concentration of field of the electromagnetic field around the slot area. This enables these fields to radiate outwards from the slot, meaning that you don't have fields being absorbed going down into the human skin, or going down into the underlying objects, as the case may be. You have the field spreading out across the area of the tag from the slot area. This leads to higher efficiency and higher available power to the chip. And also at the bottom left, you see a 4-layer phantom representing the skin, the fat, muscle, and bone, with the accompanying electrical properties, the conductivity, and the permittivity. This aids accuracy of simulation. Then you have the ASIC parameters at the bottom right. It's an NXP GX2 chip. The tag design, the return loss shows that the tag was designed to resonate at 865 megahertz. The far field plot also shows that the tag radiates in all directions, although not equally in all directions, but it has coverage in all these directions. Then you have an overview of the ink deposit and also the tattoo paper used. You can see the ink deposit, the ink receiving layer, the base layer, and the back coat layer. Then you have the specifications of the ink just under that diagram. The ideal curing condition is between 120 and 150 degrees centigrade for 30 to 60 minutes, as the case may be. So the diagrams we have here show the chip attachment process all the way to the mounting of the tag on the body. Figure one shows attaching of the chip to the tag. Figure 2 and 3 show the process of putting on an adhesive on the surface of the tag. Is a film of adhesive. 4 and 5 show peeling off of the polymer material on which the adhesive was before it was transferred to the tag. 6 shows the attachment of the chip of the tag on the body. 7 shows wetting the tag, or as soon as you wet the backing paper, you can easily peel it off from the tag. And 9 shows the final mounting of the tag on the skin. So for this robustness test, we considered 3 scenarios. The first is exercise activity at the gym, which measurements was taken after 20 minutes of gym activity. In order to ensure maximum exposure to the tag, to the body movement and sweat, the tag was placed on the torso of the individual. Then we sought to establish the effect of sweat on the tag. So here we are comparing a saline solution whose source concentration was made to be similar to what we have in sweat. We're comparing that against ordinary water in order to ensure equal measure of the liquids were put on the tag. They were put on tissue paper and to ensure even distribution over the tags. And the measurements are taken at 5 minutes intervals for a total of 30 minutes. Then also we established the effect of showering by wearing the tag and exposing to soapy water in shower for 15 minutes. This is the test equipment. It shows the performance kit. Figure 2 shows the directional coupler, while figure 3 shows the reader antenna. So this slide shows the experiment setup as well as some results. On the top left, we see the before and after gym activity image of the tag. On the bottom left, we will see the before and after read-range measurement showing that there was a drop of 13 cm after activities at the gym. At the top left shows the setup we used to determine the effect of sweat on the tag. That shows tissue paper placed on top of the tag, as can be shown on the image by the right. If you look closely, you can see the tag from underneath. Then the resistor measurements mapping for the tag is shown on the bottom right corner. Those numbers show the points of measurement, and the measurement order is also shown at the bottom of that image. So what we have here is we have the different resistor measurements from those points I showed in the previous slide. What should be pointed out here is that the most reliable results of these measurements were from the first 15 minutes, because that was when the tag was intact. After 15 minutes, the backing paper began to deteriorate, giving rise to a lot of cracks on the tag. That's what led to the spike we can see in the diagram. So, but from 0 to 15 minutes, we can see that there's little or no difference between the salt solution and water. So this indicates that there was actually no difference. There was no special influence of the sweat on the degradation of the tag during the gym activities. We also tested to see if there's any effect soap will have on the tag, and what we observed was that there was actually a 1.8 cm increase in read range, but this is a false positive, because this was because of formation of air gap between the tag and the body, which was occasioned by the weakening of the adhesion. So because of that, the formation of the air gap, the influence the body had on the tag became reduced, which led to the increase in read range observed. So as a conclusion, we will be able to say that we've been able to establish that the degradation of the tag was not as a result of sweat. Sweat did not play any particular role in the degradation of the tag. Instead is just as a result of wear and tear during the movement. Nothing can be tied specifically to the exposure of sweat. And also we can say that during shower, the tag, there was no reduction in read range measured, and there was no degradation. Instead, there was just an increase, which was occasioned by the formation of an air gap. So this is the end of my presentation. Thank you very much for your attention.